Let me give brief introduction of Professor. Professor Tzyh-Ghuang is a professor with the Department of Electrical Engineering, National Taiwan University of Science and Technology, Taiwan. He was the recipient of Poster Presentation Award in 2008 at National Workshop on Antenna Technology, Chiba, Japan. And he has also received the Dr. Wu Da-Yu Award from National Science Council, which is the most outstanding research award for young researchers in Taiwan. He is also the advisor of the honorable mention winner in the student paper competition at IEEE APS 2011. In 2012, he received the Excellent Young Engineer Award from the Chinese Institute of the Electrical Engineering. He also received the title of Distinguished Professor and the Outstanding Research Award from National Taiwan University of Science and Technology in 2012 and 2014. He is now an Associate Editor of IEEE Antennas and Wireless Propagation Letters. He is also a Senior Member of IEEE. Sir's research areas include innovative phased arrays, miniaturization of passive circuits, self-oscillating active antennas, ultra-wideband antennas, and front-end circuits and antennas for RFID applications. So I request Professor to please start the session. Thank you.
Thank you, and good morning, everyone. And it's my great pleasure and great honor to have an opportunity to in India. It's my first time to in India, and of course, it's my first time to dance on the stage. Okay, last night. Okay, so I just heard about I'm a good dancer or good actor. So I'm thinking about I will transform my roles from professor to a actor or dancer. I think it's a good idea. Okay, just a kidding. Okay, okay. And today I would like to take this opportunity to share some research, and actually it's my philosophy behind me. And it is a little bit, actually, you can read from the title. Actually, I am a guy, just I have mentioned yesterday. I'm a guy, wait, I'm a guide between the antennas and the circuits. So I'm always thinking about doing something different from the others. So that this means like actually I don't want to be a follower, follow their instruction, follow somebody's idea or follow somebody's way to deal with the antenna and the circuits. I just want to create some new thoughts, and this thought may be somehow different from the others. This is my philosophy, and I'm a guide between antenna and the microwave. So actually, I just try my best to integrate the antenna and the circuit into an active antenna or a phased array. This is the topic I would like to talking about today. Okay, and these are my experience. Of course, for the title, actually, we have now currently in Taiwan we have 5 different kind of labels. And the button is assistant professor, associate professor, professor, and then the distinguished professor and the chair professor. The distinguished professor is actually nothing more than you just get a little bit more money from the government. Yeah, it makes no difference. And actually, if you would like to be a chair professor, you must at least be an IEEE fellow. This is still far away from me. Okay, and also this is just for the service of the IEEE society, and this is the one I would like to emphasize with you and share with you. And actually, yesterday I have a deep talk with Professor Sabi, and actually. This is the one, actually, I think I really have some contribution to the society and also to the young generation because I'm the exclusive secretary of the EM education. It is not research, it's the EM education revitalization center in Taiwan. Okay, and we want to re-emphasize the EM education in Taiwan. Okay, because I think it's a global trend. Less and less people would like to study the EM theory, or even would like to study the hardware part of electrical engineering, because people tend to take the software or to the computer science. It is a global trend. But we want to revitalization the importance of EM theory. And actually, there is a word. It is not coming from me, and it is coming from a big company. And actually, yesterday, there's a gentleman asked a question: how to link the courses we studied, okay, we studied in the campus to the industry. And actually, there is a company, a big company, and maybe the top 5 PC companies in worldwide in Taiwan. It's called ASUS. I didn't know, I do not know that if you know about the name, ASUS or ASUS, ASUS. And his president said something, or not once a while, he says something. He said, for his engineering in his company, he asked them to read, to study the EM theory 30 times. 30, not 3 times, 30 times. Read, okay. The student heard about that. Okay, read 30 times. Okay, electromagnetics, and the 30 times. I still have no idea about electromagnetics, or just a kidding. Actually, you just have to. His point of view is you have to study the electromagnetics waves 30 times until you can feel the wave propagate on the printed circuit board. Okay, it is the way he think, and this is not from our for light young gentlemen. Maybe you think, hey, you guys just sit here and you just work in the campus. You can represent the industry to say the importance of the EM theory. But I think what the example I just gave to you is from the industry. This is the president of a top worldwide top company. And he said the importance of, just talking about importance of EM theory, especially the EM theory regarding to all kinds of hardware engineering, at least for hardware engineering. So actually, I'm involved deeply in this EM education center in Taiwan. We do some new ideas to generate, to inspire the students to enjoy the EM theory or EM electromagnetics more and more in the future, hopefully. And you know, if you find someone, he's the executive secretary, it means like he do everything. If I'm a project leader, I may just use my mouth, okay, to tell somebody to do the things, okay. And if you are the executive secretary, you do everything. The project leader tell me, okay. So it's a big difference. So actually, it's a heavy job, but I think I am enjoying it because I think it really help the young generation to enjoy more in electromagnetics. Okay, and oh, sorry. Okay, now let's proceed to the groups. Okay. Actually, my talk today actually consists of 2 parts. The first is a small part. It is an old problem, but we have some new idea and the new application. This is the first part. It's just a small part regarding the self-oscillating active antenna. It's just a way to integrate the antenna and with an unstable transistor. And would like to integrate them as a whole, and to hope they can find some application in wireless charging or something like that. Okay. Okay. Thank you. And then the second part will be the main topic of this talk, and it will regarding my work on synthesis transmission line and its phase array application. So I just give a quick introduction to this first part. And for the first part, actually we are talking about active antenna. And active antenna, of course, it is not a new topic. It has been studied for 20 years or even more. And many researchers focus on active antenna with different sort of different type of self-oscillating, amplifying, or low noise and no noise amplifying antenna or self-mixing antenna. And we got a new idea about the application of the active antenna. And this is related to the RFID system. And it is demonstrated, actually it is a profession, this paper is published by one of our professor, my colleague, Professor Liu. He proposed an idea that if we have a number of tags here, and actually they are out of the readable range of a reader. This is the interrogator or reader. And actually these tags are out of the acceptable range of the reader. But if we have a continuous wave source here, the continuous wave source means like actually it has not any modulation. It's just a single wave. It's just a single tone. Okay, and this continuous wave source actually can charge pump the tags and keep the tags alive. So in this sense, actually the forward link will not be a problem, and all we need is to interrogate the tags and get a backscatter signal. In this sense, we can improve the RFID system in terms of a readable range. I mean, use a continuous wave source around the tags. And we also read from another paper. It is the architecture of the tags. You can find at the front stage. It is the so-called charge pump circuit. So as long as we have a continuous wave source, actually we can charge pump the tag and keep the tag alive a week to respond to any integration from the reader. Yeah, this is the ideal. And also we have another idea. Actually, we read another paper. It is in 2012. It's talking about the passive tag to tag without the reader. It's just a tag to tag. Maybe it's a semi-active or some new sort of tag. It is a passive tag to tag communication. I mean, it means like just imagine this site. It's in a dark room. In a dark room means like there's no RFID readers. There's no interrogators. Okay, we just have two tags or two persons. And we turn on the light. The light is just a continuous wave source. It is just a continuous wave source without any modulation. We use this CW wave and we use this RF source to keep the tags awake. And then, even then, the two persons or the two tags can communicate with each other. So actually, from these two ideas, the first one is to improve the readable range of an RFID system. And the second one is to enable tag-to-tag communication. We need a low cost and low profile and lightweight, maybe low power consumption CW wave source. And it's come to us, hey, the self-oscillating active antenna could do the job because of it has a simple structure. And we can find some way to get its miniaturization, get it miniaturized, and to miniaturize it. And we maybe have a settable EIRP and won't interference with the environment. And of course, it has generally speaking, the IA has a good fast noise or something like that. But actually, the fast noise in this case, actually, it does not care. We do not really care about the fast noise, or do not really care about knocking the frequency, because it is just a free running self-oscillating active antenna. And actually, your frequency can be somehow the free running within a range. As long as it can charge pump the charge pump circuit in the tag, it's fine. It will be fine. So actually, we don't really care about the frequency. This means like we don't need the complicated phase law loop, the complicated frequency synthesizer, and we can make this solution be very simple and very low cost. And we would like to add some additional functionalities into the self-oscillating active antenna. And for this part, actually, we would like to have some frequency agility. The frequency agility means like, for example, in this environment, I found that there's interference at this frequency, then we can use the voltage-controlled self-oscillating active antenna to tune its frequency, to fine-tune its frequency to another frequency to avoid interference. And we would like to have pattern reconfigurability and to point its pattern to some specific direction for illuminating the text. This is the basic idea behind. And actually, as I have mentioned before, actually it is not a whole new topic. And it is just a topic that has been studied for 20 years. Let's just do some literature review. Actually, we have a lot of kind of active antenna. For example, the no-noise active antenna just combine a no-noise amplifier and the antenna in the receiving front end. Okay, and the self-oscillating antenna is an oscillator and the antenna get together. And the amplifier antenna, we have a power amplifier, we have antenna. Actually, I just doing some amplifier antenna with some new dot with one of my colleagues now. So it is also one of my research topic now. And also some self-mixing antenna. Okay, and among this, the self-oscillating antenna is the one we would like to talking about for now. And even for the self-oscillating oscillating antenna, actually the traditional way to integrate the antenna, you know, the AIA here means active integrated antenna. But actually, when I look back, especially I initiated this project or this research from 2008. Okay, at that time, when I look back to the so-called active integrated antenna, I have a question. Do they really integrate the antenna and the circuit? In most cases, I don't think so. Because in general, the antennas and the oscillator actually are designed independently. They just design the oscillator and then they just design the antenna. Even there is a matching network between them. And then they just have their impedance conjugate match to each other, and they say, hey, we have integrated self-oscillating active integrated antenna. This is a typical design example in the IEEE AWPL. Okay, it's called it is an integrated antenna, but in my viewpoint, this is not highly integrated. It is not highly integrated. You know, this is just an oscillator and this is just antenna, and there's a matching circuit. The size is too booky to be a real fully integrated antenna. So my thought is we would like to do something different. And this is some other examples. You have an oscillator and you have an antenna. They are not really highly integrated. It is not until this paper, actually this is a paper I read in 2008, okay? And I'm really interested with this paper. It's talking about small size aspect active integrated antenna. And in this antenna, the transistor is indirectly embedded into the radiator. In this sense, the antenna and the radiator can be integrated as a whole. This inspires me something. It means like actually we can do something similar to this, and we can reduce the size. I always want to do something, reduce the size or reduce the cost or reduce something or integrate something together. Yeah.
What will after the feedback part?
Oh, this is the feedback path. For this case, I think it is because we must satisfy the Barkhausen criteria. So actually, the feedback path, you must have an overall phase shift at the oscillation frequency, overall phase shift of 360 degrees or times and in multiple integrals.
That's the point by empathy.
The 0.5 lambda G also will serve the same purpose. So that it can avoid the length. Any sanctity of one increase?
It's a paper 6 years ago, and it's not my paper, so I didn't know exactly about why they use the 1.5 lambda G. 0.5 lambda G. I think 0.5 lambda G, if this is a 0.5 lambda G, it will be too short to connect the two patches, the two power patch, because it is an integrated patch. They just make the pitch. This is the radiating edge. This is at the radiating edge, and at this edge, it is 0 voltage. So they integrated their transistor on the center of the pitch, and it is a feedback house. Yeah, this is the way they integrate. And from this idea, actually, I think something new. But actually, then I asked my student, let's do something with some idea to integrate this idea with our RFID. I know like it is a way to improve the readable range of RFID or something. And then actually we took 1 year. We took 1 year to find a proper way to simulate this problem. Because think about it, it is not a traditional problem, antenna problem. Because it is actually, for the antenna part, I mean for the passive part, it is actually a two-pole system. It's a two-pole system. This is the source terminal, it is grounded. And this is the gate terminal, and this is the gen terminal. So it is a two-pole system. So how do you simulate a two-pole antenna system and then integrate it with the transistor and get a good prediction from the simulator for your active antenna? It is not very simple. It is not intuitive. It is not a standard simulation process. We generally take from even HFS or CST or engine alias or Keysight alias. Oh, it's he's just changing his name. So actually, we took 1 year to summarize the design procedure. And here, I would like to share with you our design procedure to how to simulate such a fully integrated. It is a really fully integrated antenna because your antenna, your transistor is completely embedded into the antenna, and the magnet antenna actually becomes a two-pole network. You have 2 ports. One is connected to the gate terminal, and the other is connected to the gen terminal. And actually, I just performed a very careful literature survey, and actually, I didn't find a way or a paper mentioned how to do such a simulation procedure of such a fully integrated antenna. So it is my design procedure. First of all, we start with the radiator, passive part. For example, we can use the HFS of CST or anything else, whatever. And we must define the two ports. And the pole impedance, we don't care about the pole impedance because the S parameters itself define the pole impedance. Okay, we just perform the two-port S parameters simulation, and you just extract the S parameters as a data item, and then you import the data item into the engine alias, for example. Maybe you use the microwave office or some other circuit emulator. It's okay. But we just import the data, import the S parameters as a data item as a load of a transistor, or the oscillator. And then you can perform the harmonic bands analysis. Once you can perform the harmonic bands analysis, you can get the oscillation frequency and the oscillation power. It's routine. It's routine. For this part, actually, it's a kind of a routine. You just get the S parameters and you substitute into the alias, and you perform the harmonic bands analysis, and then you derive the oscillation frequency and also the output of oscillation power. It is kind of routine. The most important part is you must get a good estimation about the EIRP, about the antenna gain, about the radiation pattern, and even the radiation or the conversion efficiency. Okay, so actually from the harmonic balance analysis, we take the node voltage. The node voltage means like the node voltage at the gate terminal VG and the node voltage at the drain terminal VD. And we use them as the field scaling factor, especially in this case in the HFS. We take the compress, this is a compress node, compress variable, and we take the compress node voltages as the scaling factor, and we re-enter then their parameters into the two ports of the HFS. In the port 1, it serves the excitation at the gate terminal. And at port 2, it is the excitation at the drain terminal. And we perform the simulation. And it means like the two poles are excited simultaneously with different magnitude and different phase. And the phase and the magnitude of your excitation is determined by your harmonic balance analysis. And in this way, actually, we can get a good agreement between the simulated measured, for example, antenna gain or directivity or the radiation pattern or whatever. Actually, if you do not do so, for example, you just have a two-pole radiation, and you just excited one of the pole, or you just excited the two pole simultaneously, but just within phase or out of phase, actually you will not get the accurate results. So we actually use the compressed node voltage as a reference voltage, as a reference excitation to re-excite the radiator to get a good prediction of the antenna parameters. It completes the simulation scheme. And we use this kind of, actually it takes 1 year to conclude that this simulation scheme does work. And we can use such kind of simulation scheme to integrate with and to design the outbound antenna. And there is another point of view. Another point, actually we can predict where the antenna, the active antenna or the oscillation will start. You can put, in the HFA, in the ADS, you can put an oscillation probe on the feedback loop, and then you can investigate the loop gain. It's just a standard simulation procedure in the ADS. And when the loop gain, the magnitude of the loop gain is slightly higher than 1, and the overall phase shift, because we are always talking about a feedback loop test. So if your overall phase shift is equal to 360 degrees or 0 degrees or n times 0 degrees, then the oscillation stops. In this way, even we do not perform the harmonic balance analysis, we just use a linear S parameters. Actually, we can get a good estimation about the oscillation frequency, or at least when the frequency stops. Of course, when the frequency starts is not different from the stabilized oscillation frequency. They are kind of different, but you can get a good estimation about it. And let me just give you some more specific illustration. The first step, we can estimate when the oscillation starts. And then we extracted the node voltage, the voltage at VD and the VG substituted into the HFS. You can get the radiation pattern, antenna gain, and the directivity, and so on. And then from the radiation efficient parameters, actually we can calculate the oscillation power, and we can calculate the DC to I conversion efficiency or something like that. This is the whole procedure I would like to introduce with you. And this is the routine. You can find it in many literatures. How to measure the ERP, I will just give you a quick review of the how to measure the ERP. It's quite easy. So I just go to the design example because I just mentioned about it is a small part. Okay, it is small part. I just introduce the active integrated antenna in the first, and I will move on to the major part of my presentation. And now I would like to give you some design examples. Actually, we have several designs, but this is the first one. and we published it in the IEEE TAP 2011. Just 3 years later, 3 years later, we have one of our first publication. It is a fully integrated ring antenna with a transistor. And for this design, the uniqueness is it has a acceptable EIRP and it has a acceptable DC to I conversion efficiency. But because of it is highly integrated, and actually we use some slow wave loading effects. In terms of the slow wave loading effects, we means that actually the capacitance, the parasitic capacitance at the gate terminal and also at the drain terminal actually just function as a loading capacitance to the radiator. And then you can further take advantage of the slow wave loading effect to reduce the overall size. Okay, so if you of course we add the voltage contributor to control its voltage. Let's just look up the comparison table. We made a comprehensive comparison table between our work and some others, and you can see there are many others through the 20 years. And you can find this is the smallest one in terms of the guided wavelengths, square of the guided wavelengths. Okay, it is the smallest one, and with acceptable EIRP and with acceptable DC to IF conversion efficiency. And even we calculated the so-called oscillator FOM, the figure myriad of oscillator, and it is comparable to the others, but with the smallest size. This is the first work we have presented in the past few years regarding the self-oscillating active integrated antenna. This is by one of my master students. He's a really beautiful girl. You can check the paper and you can see his photo. Okay, really beautiful girl. Okay. Okay, this is the first design example. The second design example, actually, it is a follow-on work of the first work, and actually, it is developed by one of my PhD students, Mr. Wu. Now he should get his PhD degree later on this year. And actually, this design honorable mention winner in the student paper contest. In the IEEE International Antenna and the Propagation Symposium. And it is just used ideal to increase the EIRP, use in-phase current distribution, in-phase current addition. But it is just a routine process, or it is just a simple idea. So I just skip it. I just give you a quick illustration, and it doesn't matter. And I would like to somehow for this design, actually, we just would like to reconfigure the antenna. Actually, as an associated of an AWPL, I do find that many people would like to find a way to reconfigure antenna for now. Okay, or for example, 10 papers I handle maybe 70% or 60% of the papers discussing about the reconfigured antenna. Okay, but the problem is I would like to let you know you must find some uniqueness regarding the reconfigured antenna, because it has been become a standard problem. And everybody knows how to reconfigure antenna. You just add some pin diode or some MEMS or some switches. You can reconfigure the frequency band. You can reconfigure the radiation pattern or reconfigure something. So actually, you must find your uniqueness. And my uniqueness here is we integrated the reconfigurability and the self-oscillating active antenna together. Okay, this is my uniqueness to get it published in the AWPL. I just it's not in the AW, or it's in the AWPL. Yeah, right. And we have two pin diode here. And if this pin diode is open circuit and this is short circuit, it is operated in a one wavelength wall. And if this diode is open circuit and this diode is short circuit and this diode is open circuit, then the ring will become somehow the asymmetry. and then it will operate it in the half wavelength mode. And of course, there's a spurious resonance, but actually it does not work as long as we are talking about oscillation. When the oscillation just occurred near the half wavelength mode. In this case, actually we can switch it in two states. The first state actually is in the half wavelength. Is the one wavelength mode, and the second state it is the half wavelength mode. So actually it is just two states, and we measure the results, and this is the loop gain. And from beginning, even we don't perform the harmonic balance analysis, from the loop gain, we can find this is the point where the oscillation will start. Okay, because the loop gain is slightly larger than 1. I did not indicate the parameters, the value. It is slightly larger than 1. And its phase delay, I mean the overall phase delay between the gate and the drain terminal actually exactly equal to 0. So this is the frequency the oscillation will start. And through the harmonic balance analysis, we can find the oscillation frequency, the frequency the oscillation stabilized. And of course, there will be some difference, but actually you can get a good estimation from the it just uses a linear S parameters. It does not involve the large signal or not involve the harmonic balance analysis or something else. And this is just another design example. And I would like to let me skip these cases because they are just based on the same signal. But I would like to introduce you another very interesting example. This example we just published in this year, February. And we are talking about an integrated antenna with quasi-isotropic and radiation pattern. And just think about its topology. We have, ideally speaking, it is also a loop. We have a feedback loop here. And if there are some stop loading, it is just for impedance matching. And the difference here is we have a truncated ground plane. It means like only part of the radiator, only part of the loop is shared by the ground plane. And for this part, actually, it is unshared by the ground plane. So actually, we have two kinds of radiation mechanism behind this work. The first one, of course, there is a loop antenna. It is a loop antenna. So actually, we have a magnetic dipole moment. It is a loop antenna. We have a circular, the currents in circulation. So it is a loop antenna. It is a loop antenna. And because for this arm, it is unshared by the ground plane. So the current in this arm or in this branch, it is the strongest. So there is an equivalent electrical dipole in this part of the antenna. And the combination of the two, actually, we can get almost a quasi-isotropic radiation in the, it is a three-dimensional simulated results from the HFSS. You know, the maximum to the minimum variation of the gain is less than 6 dB. It is almost a quasi-isotropic in terms of the total gain, in terms of total gain. And of course, you can design a passive radiator, even given the fact that you don't have to include the radiator. You can also get a similar radiation pattern. So it is one of the real topics we are talking about. We have quasi-isotropy. We were not talking about isotropy because isotropy is the ideal case. It is just in the ideal case we have an isotropy point source. But in this design, we almost close to the isotropy. Yeah, we just have a 6 dB difference between the smallest and the highest radiation. Between the maximum and the minimum of the radiation. And there are some parameters of it. And it has a very high conversion efficiency. It means like almost 50% of your input energy, DC energy, will convert into your RF radiation power. and it has a acceptable EIRP in my point of view, and it has a very good fast noise. It's about 100 and minus 115 dB, dBc per hertz and 1 megahertz. And this is the radiation pattern. Let me get a closer look at the radiation pattern. Actually, we separate the radiation pattern. For this part, this is radiation pattern in the SY plane, SZ plane, and the YZ plane. From this plane, actually, it is contributed by the electric dipole. And for this part, this is in the SZ plane and the SY plane, kind of different. And for this radiation pattern, it is contributed by the magnetic dipole. And just think about, we are talking about using this active antenna as a power source, to charge the tap or to charging something, to have a wireless charging. So we actually doesn't care about the polarization. We just would like to have our total electric power or total electromagnetic wave as uniform as possible in these cases. So just think about the case, if we have such kind of design, it is a quasi-isotropic design, and it is somehow installed in the space. It can cover a uniform region or nearby. Okay, so it is one of those we designed almost a quasi-isotropic radiation. Okay, there is another design. And this is the final design. Actually, it is a work by also by my student, and it is just still under review. But I think it's okay because it's just under review. I don't know the results, but I think I can share with you. And this is like a master, right? It's somehow like a master. Actually, the antenna is just here. If they are just for bias, and this is thin lines are just for radio frequency choke. And the object for the radio frequency choke is to make the bias circuit do not interfere with the antenna. And this antenna actually can have two-dimensional reconfigurability. The first dimension is the pattern reconfigurability using two-pin diode here. This is the vertical diode. This is the vertical diode, diode 2. And this is the horizontal diode or the diode 1. And upon the on and off of the diode, you can connect the monopole to the ring radiator. In this sense, actually, we can have 4 states. The first state and the fourth state are very similar. They are basically a ring radiator and maybe a ring radiator with a pair of monopole. And the second state and the third state, actually they consist of a semi-ring radiator and a monopole. In this sense, we can have a different kind of radiation pattern and even different kind of polarization. Okay, so here are some simulated results. This is for the state 1, and this is for the state 2. Basically speaking, their radiation patterns are quite similar to each other. Okay, but for the state 2, it is more like a donut-like shape. Yeah, it is a standard monopole antenna. And for the state 3, it is just a standard monopole antenna. So we just control the bias voltage of the 2 diodes. Actually, we can make our active antenna to switch its radiation pattern between 4 states. So we got the pattern reconfigurability. And furthermore, actually we have a varactor here. Of course, the varactor is controlled by a voltage, so it is actually a voltage-controlled oscillator. So actually, we have a second retunability. The second tunability means we have a frequency agility. So actually, we have a 2-dimensional of reconfigurability. The first one is pattern reconfigurability, and the second one is the frequency reconfigurability or the frequency tunability. I would say frequency tunability. So with a combination of the two, you can have a lot of application. For example, just think about the kids. If you would like to place this active antenna, for example, on the desk, you may select the state 1 because it's a radiation pattern. Maybe you would like to cover this area. And if you would like, you may select the state 2 or state 3 to cover the area. And then the other case, if you put your antenna in the corner, in the corner of the wall, then you may select the state 1 or state 4 because you can make your radiation pattern, your radiated power more directly to the space of interest. In this way, you can deploy your a space more specifically or more flexibility. We increase the flexibility. This is the way we designed our integrated antenna. Here are some results for the 4 states, their oscillation frequency and their radiation efficiency and their phase noise and their radiation patterns also. And this is just, as I have mentioned, it is just a short topic, and I would like to end up this short topic with some conclusion now. And then we will move to the long topic regarding the single-phase transmission line. For this topic, actually, I just give you some brief summary. We have a new systematic design procedure, and we have a very complex size, a very complex antenna size, and due to the slow wave loading effect or something. And we have a good radiation or oscillation characteristics, and we have a two-dimensional recoverability. And the future work to be verified by my student is to verify that it can improve the readable range of alpha. This is what I asked him to do before he finished his PhD program. And we even would like to use this kind of design to enable tech-to-tech communication in a reality environment. This is the first topic I would like to share with you. Maybe I will take a short break here to answer any question, or I could interact with you with this topic. It is just a short topic. I would like you to ask some feedback from you. Okay. And sorry, like sometimes for me, it is not easy to catch up the question because of the accent. Sorry, because so maybe you could use it a little bit slower, and I will try my best.
Thank you, sir. I want to know when you want to transistor you introduced, no? If you are increasing the gain, what will happen effect of the antenna gain directivity radiation?
Okay. So your question is how to increase the antenna gain?
Gain, transistor gain.
Yeah.
If I am increasing the
yeah, it is actually a good question. Actually, if you want to, I think it's a channel between your size and your gain. It is definitely a channel. So if you miniaturize the size, you will say it has at a sacrifice of the gain. So there's two ways to improve the antenna gain. The first one, actually, for the active antenna, we don't care about the gain. We just care about the EIRP. EIRP. That is the gain times the rate output oscillation power. So there are two ways. The first one, increase the gain. But increase the gain means that you increase the size, right? You increase the antenna aperture, then you can have you can increase the gain. This is the first solution. The second solution, you increase the output oscillation power. So to increase the output oscillation power, you must have a better matrix between the antenna and the oscillator, the transistor, or you choose another oscillator. And the third point, we are just doing something like regarding to this, is to use multiple active antenna and then connect it between using some mutual coupling. Using some mutual coupling, and you integrate the antenna and you have some mutual coupling, their frequency can be locked and then your gain can be increased. This is my point of view to reply to your question.
Thank you, sir. Thank you.
Okay, so it's a
Hello. Sir, in one of the slides you have mentioned transistor model from NEC. Is it the same NEC NEC2 MOM based software which is used for wire antennas, or is it different software?
okay. It is another question. You asked what will be the case if you use a different simulator, right? Yeah, is it a problem you asked?
I want to know what is NEC.
What is the
NEC, you mentioned in one of your slide transistor models from NEC.
Oh, okay. You'd like to know the model of the NEC transistor.
Yes, what
actually,
is what?
actually we just download the model from the website of NEC. Yeah.
If they give the S1 and other these parameters for modeling the transistor, so whenever you incorporate the basic circuit with other lead resistance, etc., has to be incorporated to get the actual S1 and S2 parameters. So
Yeah.
it is the basic transistor model in a form to be accommodated for circuit application while simulation, taking consideration in any of your software, ADS or whatever it may be. It's a basically model. It's a manufacturer, they have supplied the model. For
Yeah. So
no, it's not software, it is for this purpose.
yeah. It is not our responsibility.
Because in
but-
Foundry, when it will go for
Yeah,
this
that's
application, it will come with some package thing. This have some circuit, lead resistance, inductance, etc. It will come with all these things and its frequency response, so that you can model this thing. You have to incorporate how much gain at what frequency gain. If you have to compensate what this, all these things it will come.
But actually, to be frank with you, actually, I think the modeling from the manufacturer, actually, especially for the discrete elements, they are not accurate enough. So actually, there are always some discrepancy between your simulated and major results. And now, currently, I'm just doing some job with my colleague, who is an active guy, a real active guy, and in the integrated circuit. We just use our TSMC. You know, TSMC is the top one manufacturer foundry in worldwide. We just use their model. Their model very accuracy. We just are doing similar things on chip, and we use the process of CMOS 0.18 micrometer. I think the cadence is 0.18 cadence or something else, and integrated with a special topic I will introduce you later. It's called IPD. Integrated passive device process. We fabricated antenna on the integrated passive device process, and we fabricated a transistor on the CMOS process, and we use a free chip and integrate them together. In this sense, we will get a better estimation of the transistor model, because actually the manufacturer, the model provided by the manufacturer, in general, they will not in good agreement with your simulated result, especially in terms of a bias voltage or something like that. So, yeah, this is my experience. Yeah. Any other question? Okay, if no question, then I will go to the second topic. Okay, second topic. Okay, thank you. And the second topic actually is a more exciting or more interesting topic in my point of view. In my personal point of view, it's a more interesting topic. I would like to introduce you how to integrate the feeding network of multiple phase arrays together as a whole. It is a topic more related to microwave circuit, but we just use the way the way we deal with the microwave circuit to the phase array, and we would like to integrate make a phase array, the feeding network of a phase array, multi-functional. It is my objective. And actually, we are just preparing our first book regarding this topic, and it has been under contract by the Wiley and Sons, and hopefully this book will be finished next year and will be published 2 years later. Okay, it will be 2016 or something. and we will have our first book finished and published. And this is exactly the topic talking about the synthesis transmission line and talking about the phase array application of synthesis transmission line. So since we are talking about the so-called synthesis transmission line, let me just give you a brief review. Oh, before I give you the brief review, I just talking about, when I talking about this part of technical program of technical issues, actually, I will just also introduce you several important things in your life to do. You have to do in your life. Because in these things, you can later on figure out, you can create something new. You can create something new. I will introduce step by step, okay? And you'll find it is just a daily life. It is not related to the so-called the technical issue, but your daily life could impact your career. Otherwise, I will not stand here to introduce this part, because all these parts actually just come up one date, and I will introduce later. Okay. Anyway, first of all, I will just give you a brief introduction, a brief review about this concept of slow wave, and then I will discuss some traditional way to make things miniaturized. And then I would like to introduce you the so-called synthesis transmission line. Actually, the synthesis transmission line itself is not a new topic at all. Also, it is just some people call it is an artificial transmission line, and some people call it is a synthetic transmission line or synthesis transmission line. It is also not a new topic, but it is the it is our thought to make the synthesis transmission line have a dual operational mode or tri-operational mode, and making it distinctive and making it different from the other works, and making it to have the ability to integrate multiple feeding networks of multiple arrays as a whole. It is our objective. So that's what time is it? Is it a break time? No, it's just 1 hour, right? It's because my okay. Okay, it's just we just have 25 minutes to the break. Okay, it's okay. Okay, now I will just start the topic to introduce the concept of slow wave. Just think about the so-called wave propagation and the wave propagation, the free space wave propagation, and the wave propagation of the electrostatic model of wave propagation. Just think about that. The similarity of the two things. I think you guys must be very familiar with this equation. This is a typical Maxwell equation. And we solve the wave equation, we have the phase velocity, right? The phase velocity is equal to the square root of mu times epsilon. And in the electrostatic model, I mean, for example, you propagate in a pair. And in these cases, actually, your electric field can be reduced to a scalar vector. It's called voltage. And your magnetic field is related to the current. And your permeability and the permittivity actually can be related to the per unit length, inductance, and the capacitance. And in this sense, actually, your phase velocity is determined by the square root of L times C. This is the basic principle between the electromagnetic wave propagation and the wave propagated in a quasi-static or a TM transmission line. Yeah, it is well known. And this is the basic concept of the so-called slow wave. Okay, and I'm just in case you are not familiar with this, you are pure antenna guy, and you are not familiar with the concept of slow wave. So I just give you some brief review. And sorry about if you are already have some concept about the idea of slow wave. Okay, so this is the linkage between the Maxwell equation, the electromagnetic field, and the voltage, and the inductance, and the permeability, and so on. This is a misspelling by my student. It's a misspelling. Okay, okay. Then we under the assumption of TEM wave transmission. Actually, we can solve the equation. It's a standard equation. And for this kind of equation, you can figure out the so-called characteristic impedance, right? The characteristic impedance of the transmission line. And you can define the so-called phase velocity, phase constant or the wave number of such kind of a transmission line. Now, just think about the case. What would be the case if your inductance and your capacitance rises proportionally? If the inductance and your capacitance rises proportionally, actually your characteristic impedance will remain unchanged. Okay, but your phase constant will rise proportionally to the inductance and to the capacitance value. And in this sense, your phase velocity will decrease. Sorry, it is a miss arrow. Yeah, your phase velocity will decrease, and your wavelength will decrease. It means like in terms of the physical size, you can use a smaller physical size to realize your circuit, as long as you have inductive loading and has a capacitive loading at the same time to keep your characteristic impedance unchanged. And in this end, at the same time, your phase velocity will decrease, and your guiding wavelength will drop. So there is a mirror to measure the capability of a spatial structure or to to make the wave as slow as possible, something like that. I mean, the slow wave or miniaturization capability is called the slow wave factor. And the slow wave factor is defined very simple. It's just a ratio between your guiding wavelength and the ratio of the free space wavelengths. You can figure out that as long as your guiding wavelength is very small, then your slow wave factor will be very high. In our experience, in our thin transmission line, in general, our slow wave factor could be about 10 in PCB design, and it could be about 100 or about 80 or something in integrated circuit design, and I will introduce you later on. So actually, when my first time to get involved in this topic, I mean in the thin transmission line, actually our goal is very simple. We just want to miniaturize the size because it is a project from the company, and he is doing something in the UHF band RFID. And in that frequency band, because the guiding wavelength is about 30 or 20 centimeters, it's too large. They need some way to miniaturize the size. So in this sense, we need a way to miniaturize the size. And that's why we begin our study of the synthesis transmission line. And at night time, it is about 2007. At night time, I cannot imagine this topic could last so long until now. We're still involved in some new design regarding the synthesis transmission line and its phase array application. Yeah, it is a long story, and let me tell you the long story step by step. And then last, I will introduce you some typical way to get the slow wave loading effect, or the so-called ways to get miniaturization. Okay, the SIR, the state impedance resonator, is the most typical way, one of the typical way to get a little bit size reduction, and it also, of course, can push away the harmonic resonance to a higher frequency, or introduce a dual band or tri-band operation or something else. And of course, you can use a metamaterial line or the composite right-handed line. to realize the so-called circuit miniaturization. And there's another technique called complementary conducting strip. Do you guys know the so-called complementary conducting strip? It is called CCS. Is anybody know about the idea about CCS? Okay, I will introduce a little bit. Okay, let me just first from the step impedance resonator. It is a very simple. It's a standard in a textbook, right? You have a variation of your impedance along a transmission line. Then you can control the second resonant frequency of the resonator. And then you can push away your resonant frequency to a desired frequency. For example, it is 2-3 times or 3 point something times from the fundamental frequency. In this way, you can have a wide stop. It has been widely used in the filter design. And this is some typical design. It's just like an art or something. But it is a filter. It is a filter, and it has some kind of capability to miniaturize the circuit size. Yeah, it indeed, in addition to push the sphere frequency, it can also has some sort of miniaturization. And this is the first one. Of course, the composite line right hand, the metal material, or the lines, or the metal material lines, it has been well known by the people for 10 years. It is probably I would say it is the most important most important topic in the past decades to impact our antenna and also to impact the microwave community. Because we found that the metal material lines actually can do a lot of things. And actually, I myself involved in some kind of metal material lines, and to combine with our slow and thickness transmission line, you will see later on. Okay, and this is a typical configuration of a composite right-handed transmission line after Professor Tatsuo Ito. Okay, and this you can use it to reduce the size or to design a beam scaling phase array or something else. This is the so-called metal material line. I just gave you a brief concept or brief introduction. And this is the so-called CCS. Okay, the CCS complementary conducting strip is a two-dimensional routing of the transmission line. A two-dimensional routing with some kind of capacitive and inductive loading. This is a capacitive loading, and this is a inductive. This is a capacitive loading, and this is inductive loading, to my understanding. And this concept is after Professor Tzyh-Ghuang Zhuang, Clivo Tzyh-Ghuang. Actually, he is the former chief in edit of IEEE microwave and MWCL microwave components and wireless and components later. And he is also an outstanding professor in Taiwan. Okay, and this CCS structure actually is especially suitable for CMOS implementation. Because of it has a two-dimensional, very tight routing without very serious coupling between the lines, and also it has a comparable Q. It is a acceptable Q. You think about the case like the CMOS design, it has a it is a poor Q factor. In general, it will have poor Q factor for the transmission line and for your inductance. But for this design, actually, you can get a compromise between the size and between the quality factor and between your fabrication process or something like that. In this case, it is outstanding, and this is a rarest copper. Just think it is a rarest copper, and in this case, it is a mixer or something. Okay, it is one of the design. And actually, we do some two-dimensional thickness transmission now, but and the results I cannot disclose now. But I think the results will be disclosed in our book. Okay, we also do some two-dimensional thickness transmission, but it is not popular. I would like to introduce you in these cases. And here are the thickness transmission line. And for some unknown reason, this professor do an interesting job. In 2012, he published a paper in IET microwave antennas and propagation. And he, for some unknown reason, summarized all kinds of thicknesses transmission lines. So you can think, hey, just like an antenna, as long as you have a unique pattern, you can have some slow wave loading. For example, for these cases, this is a capacitive loading. You increase the capacitance. And this thin lines is the inductive loading. And this is the inductive loading. It is inductive loading. Okay? So if you combine, increase your capacitive loading, you increase your inductive loading, your slow wave factor will become increases and you can reduce the size. So actually, there has been already a lot of slow wave synthesis transmission line. Not to mention the metamaterial line. Just think about the slow wave right-handed synthesis transmission. There has been a lot of work. This is ours, just one of them. So what is the uniqueness of our design among these, for example, 45 designs? Actually, we would like to have the synthesis transmission to be multi-mode operation, multi-operational mode. And this is the birth of our first transmission line. It is you can trace back to the MTT on 2007. It is just very simple. We just want to increase after this publication, and this is by somebody else in 2005. At that time, I just joined the faculty of the National Taiwan University of Science and Technology, which is the university I served as a professor there. And this is in the summer. I read a paper, and I found, hey, there's something interesting. At that time, just almost 10 years ago. And it is just a periodic slow wave loading, and capacitive and inductive, capacitive, inductive, capacitive. And then let me think, and I asked my student, is it possible we use a non-periodic structure? It is a periodic structure, but is it possible we use a non-periodic structure and we further increase the inductance value, and we further increase the capacitance value, and we can still achieve the so-called thickness transmission? The answer is yes, we can. And then we published our first paper on the MTMTT. It is just based on a simple methodology. You increase your inductance value in terms of a meander line, and you increase your capacitance value by parallel plate capacitance and interdigital capacitance. And actually, you can figure out when you introduce your the interdigital capacitance, there is a parallel LC tank, and using this parallel LC tank, you can suppress the higher order modes. This is just the first work, and later on, I termed it phase 1. We just replace conventional transmission lines by our thickness transmission line. And using this way, actually we can do a lot of work. We can design a branch line coupler. We can design a reverse coupler. We can design a bottom matrix or something else. But actually, we just replace the line, conventional line, by synthesis transmission. It is kind of boring. I think so. I don't think so. And the second phase, I'd like to do some coupling between the lines. So the second phase, I would like to have our synthesis line have some kind of coupling. So, for example, this is a matching balance, and this is a ring filter, and this is I think it is just a couple line or something like that. And this is the fast tool. We want our synthesis transmission line be coupled to each other. Okay, that's all. And after the phase 1 and after the phase 3, I asked myself, I'm a guy, not very interested in doing the same thing for years, okay? So I keep asking myself for something. Oh, well, our synthesis transmission line has the mirror of a very complex size, has the mirror of a harmonic separation, for example, has a mirror of a high capacity to the other circuit, and then we have actually we have some formulation, we have a systematic design equation or something like that. But what else? How where is the way to make our design to be unique among these so many synthesis transmission lines? It's because our design is just one of the, for example, 45. It's easy to think how to make our design to be unique when you compare to all other kind of synthesis transmission. It comes up to my mind, and someday I just give you a very important activity in your life, just taking a shower. Okay, just taking a shower. Someday when I taking a shower, sometimes some new ideas come up to my mind. Some new idea come out of that. Hey, why not we make our transmission line to be multifunctional? To be multifunctional, I will define the so-called multifunctional later on in our just in the following slides. I would like to have our synthesis transmission line to become multifunctional. And then we can use the synthesis transmission line to become the core building block in some array application. So this is the core terminology of the core part of our discussion. So let me just, before the break, let me just brief introduction of the so-called, we just take the dual operational mode synthesis transmission line as an example. I abbreviate it as a dual mode, but be careful here, the mode, not maybe I should use the term state, because actually we are not talking about a physical mode. We are just talking about the operational mode. And the so-called dual mode, actually, or dual operational mode, is actually quite simple. We just want as our transmission line to have different frequency response. For example, at 2 frequency or at 3 frequency. So their ideal is very simple. But actually, it is different from the other guys who deal with the filters. We do care about the characteristic impedance. We do care about the phase, and we do care about the so-called the open circuit or the phase response in the open circuit in the stopper. Now, let me just give you some example. For example, for one dual mode, a dual operational mode synthesis transmission line, I can have a line at 1 frequency. It is a 50 ohm plus 90-degree line. So it is a 50 ohm line, and it is a 90-degree line. Okay, in 1 frequency band, and in the other frequency band, it must be open circuit. Of course, this is our first version of design, so the open circuit is not so perfect. But this is the basic idea. I would like to have a line to be well matched in one band, and we specify its electrical length to be 90-degree also. And in the other band, it should be open circuit. And for the other line here, we would like to have the line to be a 35 ohm and a 90-degree line in 1 frequency band, and to be 50 ohm and either 50 ohm with some other fast delay in the other band. Okay, and then in the third line, we would like to have the line to have a 35 ohm characteristic impedance, and its fast delay must be 90-degree. And then in the second band, it must be open circuit. So there are some points to be discussed here. First of all, Many people ask me or ask my group a question. What is the difference between your ideal and those guys deal with the filter thickness theory? Okay, because actually think about these cases. You just have a low pass filter. You just have a low pass filter, right? In a low frequency band, it is a pass band with a specific characteristic impedance. And in a pass in a stop band, you will have a transmission zero, right? It is just similar to the filter thickness theory. It is the first question. And our answer to this question is actually in contrast to the filter thickness theory, actually we deal with the phase. We deal with the phase. In terms of the filter thickness theory, in generally they don't care about the phase. They just care about, for example, just think about the insertion loss method. They just care about the amplitude response, the insertion loss response. If you are talking about transmission zero, who cares about the phase of the transmission zero? As long as the signal cannot pass through, it is a transmission zero. But it is not the case here. For our case, if we have a transmission zero, we enforce the phase of the transmission zero must be 100, sorry, not 100, must be 360 degrees. That is 0 degree, that is open circuit. We must have the input impedance of this building block be open circuit at a specific frequency. That makes difference, makes our thickness transmission line somehow different from the conventional filter thickness theory. And the second point, just think about, also think about this kind of transmission line. In traditional filter thickness theory, actually in the passband, even in the passband, they don't care about the phase. They don't care about the phase. They just care about the linearity or the group delay. Fine. Okay, in a filter, the group delay should be as flat as possible, nice all. But they don't care about the exact phase of your or the propagation delay of your filter. But in our case, we treat it as, although if you use a long circuit model, it's just like a filter. But actually, we treat it as a transmission line. And we treat it as a transmission line. We use the transmission line equation, and we control the phase. We control the phase in one frequency band, and even in our recent design. I'm not disclosing the recent design in this talk, but maybe you can read our papers in some days later. We control the phases, and we control the impedance in dual and even tri-frequency bands. In this sense, actually, thickness or the dual operational mode thickness transmission line indeed is somehow different from the filter thickness theory. This is the first point where I would like to emphasize. The second point is we use the right-handed method, that is slow wave approach, to achieve the so-called dual mode transmission line. In a low band, in general, it is a pass band. And in a high band, it is a transmission zero with open circuit input impedance. But actually, ideal can be reversed. And actually, one of my students just finished the work. We use metamaterial or use left-handed line. Or in other words, it is just a high-pass filter. Okay, in that case, you can have a transmission zero. And at the frequency of the transmission zero, your input impedance, for looking into either side of the network, should be open circuit at a certain frequency. And in the high frequency, it becomes a pass band. So the response will be reversed. In the low band, it is a transmission zero and with infinite input impedance. And in the high band, it becomes a pass band. So let me ask you a question before our tea break. Why, for this sort of thickness transmission line, we would like to make this building block have input or open circuit input impedance when looking into either side of the circuit at a certain frequency. Did you guys have any idea about it? Why we need to have the input impedance of this building block be open circuit at a certain frequency? Do you guys ever just raise your hand? I just want to make our discussion interactive. So just think about why we would like to have, especially just think about the goal of this design is to make multiple phase array, the feeding network or multiple phase array to be integrated together. So just think about why we need to have the input impedance of our circuit to be open circuit at certain frequency. Why? So the answer is we want to make this building block become invisible at a certain frequency. Become invisible because open circuit means invisible. So if at a certain frequency, when you're looking either in this port or in looking into this port, it becomes infinite input impedance, open circuit. It means like this building block is invisible. So in this sense, we can design a complicated feeding network, and some part of the network will be automatically become invisible at a certain frequency. In this sense, we don't need any switch. We don't need any maps. We don't need any pin diode. We don't need any active devices. But we can change the feeding topology from one network to the other network upon your operating frequency. This is actually, before the tea break, I just give you the big hint about our works. This is why we can combine the multiple feeding networks or phase array together. Actually, this is the key idea. We make our building block become invisible in certain part of the frequency or at a certain frequency. And of course, you can make your input impedance become short circuit. You can ask me why it should be open circuit. Is it okay to be open circuit, short circuit? My answer is okay. If you use short circuit, it means like anything cannot penetrate through. Any signal cannot be penetrated through. So if it is a short circuit, it means like it will be shunted all signal, virtual shunted all signal. So generally, we don't like to use the short circuit. We just use open circuit to make some part of the circuit become invisible. Okay, I think it's about time to tea break, and I will resume our discussion later on after the half-hour tea break, and then we will go back to finish the second part of our discussion. Thank you. Thank you.
Thank you, sir. So now there is a half an hour tea break. So we will again assemble at 11 and then continue with the same. Now there is an announcement from now, today onwards, for the food coupons will be applicable. So the coupon